Hello everyone. Today I will introduce Card-stunt as a service. It is a new mobile crowd service for a massively packed crowd to enable instant collective visualization. You might have seen this kind of collective performances before. This is called a Card-stunt. It is a very impactful way to visually convey a message of the crowd. But we already knew that. Yes, it is really hard to do this. Card-stunt cast enables this kind of performances by simply holding up their smartphones overhead. In the night, smartphones automatically glow on and off based on their relative locations. Under daylight, participants simply click their cardboard upon a cue from their smartphone. Imagine this massive candlelight visual. What if they hold not just candlelight, but their phones? We envision that such a massively packed crowd uses our cats to convey their messages to the world. The messages can be anything: to support a sports team in a stadium, or to mourn victims of a disaster, or it can be a message of a protesting to make the world a better place. To this end, we realize that the key feature is instant, accurate, scale-up localization. First, the crowd localization should be an infrastructure-free technique. A crowd can assemble anywhere, such as a public square, a stadium, or street. We cannot expect all places to have the dedicated infrastructure for a crowd localization. So, some localization infrastructures such as beacons are not an option. And according to our research, an average distance between adjacent people is about 75 centimeters. This means that crowd localization should support a decimeter level accuracy. Therefore, the GPS on most commodity smartphones are not an option. Lastly, the whole crowd localization time must be short enough for not only for tens of people, but scalable to hundreds of thousands of people. Existing techniques for localization have used sound or wireless signals to measure a distance between two devices, and they localize the devices using triangulation. But the problem is to make it quick enough on the scale and density. It is hard to transmit all the signals at the same time for a densely packed crowd due to interference and limited channel capacity. So, transmitting the signals should be serialized. This way, the time will not be scalable to the number of devices. We present visualized simultaneous multi-target angle of arrival sensing for crowd localization. While a phone screen emits visualized signals, a back camera of another phone captures the signal and calculates the angle of arrival. The beauty is that, unlike sound or wireless, visualized signals are favorable to simultaneous multi-target sensing, thanks to its extremely directional property and low interference in between. I will briefly introduce the CAS architecture and its workflow. First, participants hold their smartphones overhead. Then each smartphone simultaneously its own identifier as a hue transition sequence as shown in this video. At the same time, its back camera captures other identifiers and calculates the angle of arrivals. Using all the AOA observations, the CAS server reconstructs the locations of all devices and assigns a pixel to each device at the right position. That's all. A collective visualization will be automatically done by CAS. You may be curious about holding their smartphones overhead. The reason is that to maximize the line of sight transition between cameras and screens. It may seem burdensome, but we believe that it is not a big deal for a highly motivated crowd. and they don't have to hold up the force for more than a few seconds. So let's talk about technical challenges to realize CAS. Each device emits its own identifier as a hue transition sequence. But what happens in reality? What does it look like? These phone screens are not enough. They display some colors, but the color captures only black. It is because of the auto exposure feature. The problem is the same in the night. It captures the white saturated color on the screen. To address this problem, CAS reconfigures the exposure settings to be optimal under diverse lighting conditions. But another problem comes out. During a hue transition, a camera often captures a wrong hue value, like this example, capturing yellow during green to red transition. It is known as the rolling shutter effect. Most imaging sensors today capture a frame by rapidly scanning pixels in one direction. The side effect of doing this makes not intended hue transition. We filter out this anomaly by exploiting characteristics of the rolling shutter effect, such as this anomaly is seen only in a single frame, and the wrong color is a mixture color of the previous and the next color. Then CAS captures a device ID at less than 30% of error under most conditions, even at a distance, and mostly in the night and day. To increase the chance of reading a correct device ID, CAS repeatedly transmits the device ID. We found that repeating 25 times is practically good enough, considering the time to hold the force and the final error rate. Once correct device ID is observed, CAS calculates the interval of arrival. We evaluate the A-wave accuracy by mounting the two devices on the tripod by varying broadcast angles and distances. As you can see, even under a random device orientation emulating handheld situation, the error is less than 32 degrees regardless of lighting conditions. From now on, I will talk about how to reconstruct all locations of devices using AUA data. When the observing device DI measures AUA to the target device DJ, the center RJ, the target device is located in the visible region due to the intrinsic error of AUA. Then the visual regions are overlapped by multiple AUA observation. At this time, the target device is located where it minimizes the cost function defined by the difference between the original observed N waves and the derived N waves. This may look like a straightforward optimization problem, but we found that the real problem is accuracy and time. We tested the optimization problem under this setting. Given the broadcast locations, the localization results are not much accurate, as you can see. We found that the localization error comes from two factors. First, we compensated random orientation using built-in sensors, but it is not perfect due to the intrinsic error of the past sensors. So we introduced an additional error term to the optimization problem. Now, it looks better, but not great yet. In our design, we assume that the camera is located at the center of the phone, but yes, a back camera is located at here. We adjust the camera position term by approximating the off-center distance as a half of the screen size. Finally, it looks great, doesn't it? CAS maintains high accuracies under diverse settings, different lighting conditions, and random home placement. Now, I will show the scalability issue in computation optimization time to solve the optimization problem for a large crowd. Let's say you have 100 devices or less. It's fine. It takes about 10 seconds. But for 900 devices, it takes more than 2,000 seconds. We found that such a long completion time is resulting from the non-polynomial nature of our optimization problem. So we approximate the optimization problem as a quadratic form. Then CAS significantly reduces the completion time, but the quadratic optimization gives less accurate results. So CAS uses the non-linear optimization to precisely assign each pixel for a small crowd. Otherwise, for a large crowd, the completion time must be short enough. So CAS uses the quadratic optimization. Then you are happy with 1,000 people. It takes less than 10 seconds. But what about 10,000? Even with the quadratic optimization, it takes more than 100 seconds for 10,000 devices. Our problem is in the level of parallelism, thanks to the locality of AOA observations. The question is how to partition them into subgroups of devices close to each other, more exactly preserving observations in between each other. Look at this matrix showing observations between each devices. You see the observations between closely located devices are together everywhere. CAS uses the RCMP ordering algorithm. Then it can find partitions preserving most observations locality inside. Now, CAS parallel solve the small size problems and stitches the sum results, giving the final results. This strategy works nicely. For 10,000, it takes less than 8 seconds. We deployed CAS on 49 participants in the night and day under the real-world diversity. With CAS, the participant is successfully collecting visualization for national services. Even they fully choose where to stand and hold their smartphones overhead by hand. See, CAS achieves less than only 15 centimeter errors. We conducted many other experiments under diverse real-world conditions. Please refer to our paper for more details. Let me conclude today's talk. We propose a new mobile cloud service, CAS, to enable instant collecting performances for massively connected cloud in the real world. We implemented CAS on commodity smartphones and cloud server by addressing technical challenges of instant, accurate, serial localization for massively packed cloud. Who will benefit from CAS? It can be any cloud, such as fans of a sports team or the broadcasters who dream of a better place. I would say if people want to speak something to the world, they must be able to do so. CAS will have contributed. We believe CAS will open up a new zone of social media for people in the real world. We will demonstrate CAS in demonstration. Please come forward.